started. My talk will be about HPC software engineering, ensuring high performance and high quality software during the full development cycle. We'll start out with a general introduction, thereafter go into the hardware lifetime of our HPCs, the lifetime of the software on the HPCs, then combine the two and find some challenges, and thereafter get why we've got this mini-symposium and what we've got as content in this mini-symposium. And dear me, I wanted to start a timer lest I hog all the time here. Okay, so the general introduction. So as you might know from the TLR perspective, aircraft and flying are very relevant. And one of the culprits there is these typically use combustion engines. And there the European Union set the Fly Past 2050 goals, which state that there should be until 2050 a 3/4 reduction in CO2 emissions, 90% in nitrogen oxide, 2/3 in noise, and that will require quite different aircraft designs, as seen on the right here, for instance, either going towards electrifying on the top or on the bottom there, even more unusual shapes of aircraft. And these unusual shapes of aircraft need to be designed, developed, and certified. And all of these will require simulation because generating fresh aircraft designs and not even verifying whether they work is out of the box. Getting them certified, so building these here, doing a test flight, and then finding out they don't work is also not appreciated. So fast simulation is key here, especially with optimization in mind. So the NASA had a vision for that called CFD Vision 2030. Their goal was to fully resolve the flows of an aircraft. For instance, in the top they're seeing an aircraft in full flight and vortices being shedded around it. They wanted to go towards scale resolving simulations and set that as a goal to 2030. And there they found that we currently lack a few things, which is advances in models such as turbulence models, advances in the time-stepping algorithms or algorithms in general, advances in the HPC hardware, and advances in the parallelization methods on that hardware. And only if there are sufficient advances in all of these categories will we be able to do a fully scale resolving simulation of an aircraft. Till 2030, of course. And if we now go towards the industry perspective, where we might just want to use two equation models for landing and high lift configurations, let's say A380 with 50 million grid points, using a low speed configuration, K omega, and so on, that already had 50 million grid points in 2006. The simulations are getting larger. XRF1 had 100 million grid points 2020, and the industry is moving towards larger simulations there, with the goal, of course, of having the same turnaround time and more details at the same time. And again, for that we need faster hardware and faster software. And for the hardware part, there's progress here. So going back a few decades, in 1999, the largest TLR cluster had 12 cores. Then hopping forward to the next cluster in 2007, that had Opterons in there, 128 cores. And then going to one of the two current clusters called Kara, stationed in Dresden, that has got 146,000 cores, including a hierarchical structure, so network, multiple nodes, 2 sockets per node, CC NUMA on the node, and accelerator cards. Okay, so we had quite some right there, going from very simple to now very intricate designs. So, of course, generating code for intricate designs is hard. So first, let's look at the hardware lifetimes that we had. Example here again, the Kara cluster. Like I said, around 146,000 nodes at the start. Sorry, 146,000 cores at the start. Start just comprising AMD EPYC cores, AMD EPYC processors, 2 sockets per node, very traditional setup. There you have 8 NUMA domains on a node. You've got shared L3 cache between 4 cores, shared memory lane between 8 cores. So you already have to deal with quite a bit to get a code that uses MPI and OpenMP to work well on that machine. Then the cluster started 2019 will run until approximately 2025. So still 1 year to run, so 6 years runtime. In between, we had a sister cluster brought up in Göttingen, very, very similar. Added a second stage, adding mainly more nodes using the Zen 2 architecture, and had other small additions such as a GPU partition and a Gracehopper partition being added. Okay, so 6 years runtime mostly. And the next iteration is already planned, containing a higher memory partition, traditional x86 there to be able to use commercial codes. So main target, large-scale FEM simulations. And thereafter, a main partition targeted at CFD applications. There we have a lower memory requirement, and the architecture is whatever performs best for our codes. So we have a bit more freedom compared to the previous cluster. Okay, but main gist, 6 years runtime for a cluster, and thereafter you get a vastly different cluster, and we need to deal with that. So what does this software do meanwhile? This year we already had all these simulations here were carried out with the tau code of DLR. The first publication for that was 1997. That was an MPI parallel code, being able to work on unstructured grids. And from today's perspective, it is designed for relatively low process counts. Because in 1997, we had, well, let's say 12-ish cores to deal with. Current clusters have a few more cores. The current date is 2024, so 27 years up and running. The code is still under development and very much still in active use at DLR, at Airbus, at quite a few universities and other industrial partners in Germany and Europe. But the successor is already under development. That's just so you have heard of it. There's a cooperation between DLR, Honora, and Airbus to generate a next generation CFD code called CFD for Honora, DLR, and Airbus, for short, CODA. Okay. That is already under development and is joined by quite a few partners in Europe, with the main partners being shown on top here, being Honora, DLR, and Airbus, and then quite a few research partners such as HLRS, Surfax, IAG, TUM, and so on being in the list here. Mind, this list here is around 3 years old. We now have quite a few more. And the code will, compared to tau, have quite a few more features, such as high order for the flow solver, such as discontinuous Gagliarkian and discontinuous Gagliarkian spectral element methods, overset grids, so a revamp of the Chimera approach, rapid CFD, so IBM, so we don't have to do meshing, grid adaptation to refine the mesh where we need it, and thereafter full multi-grid for the nonlinear part as well. Okay. But main gist here, tau already is alive for 27 years and running into its 30 soon. CODA started 2014 around, so 10 years. That will also run for quite some time. And there comes a challenge with that. That is, our clusters live, if everything goes well, 6 years. Our codes don't. They live for 30 years if they're industrial codes. So codes have to work on many clusters. If we just have one cluster, it would be 5. If they have to work for different partners, there's a plethora of clusters they have to work on. And that brings us different kinds of hardware. Easiest option, think x86 versus ARM. Second one, think accelerator cards. I started my PhD around 2012. Back in those days, the many integrated cores architecture was very much in vogue. That's converged to GPUs nowadays, but still something to keep in mind when programming a code. They have to go not through one here, but maybe through many different iterations to work on the current clusters. And then, of course, the difference in scale, 1997, 12 cores, and now, well, a nice factor of 1,000 in there if you were to use the whole machine. And that doesn't account for the codes always being under active development, meaning researchers want to implement new features, be it newer LES models, new boundary conditions, new ways to implement them. So new features get added, and all of them can, and trust me, will impact performance and scalability. And old features might become broken. Think of cluster-specific optimizations. Think different communication patterns for specific choice of networks. And that is where all of us here come in. Because somehow we need to deal with all of those developments, and just developing does not lead to a working code that works on other clusters. There, we first need to do testing, which means testing whether the code is still correct, whether it has got scalability regressions compared to the last version, whether they've got node level performance regressions compared to the last version. And that just gives us information. We also have to actually do something about them. Improve to regain set correctness, scalability, node level performance. And that requires something, and that is software engineering to gain towards that, testing, easy adaptation of the code, and improving it. And that directly brings us to the name of the Mini-Symposium and the contents thereof. Because over the whole lifetime of the code, we need to do stuff. That is, debug, test, and find issues. Performance analysis, we will have 2 talks about that. Then we have to somehow track whether we have got the same performance we had a year ago or whether something went horribly wrong. So we need to instantiate continuous performance monitoring and testing for the code. Then, often unappreciated, someone needs to be able to install your code. Yes, that sounds easy. Trust me, it ain't. I just say, use Petsy, which version? And last but not least, someone needs to thereafter get the jobs into the queue and ensure that they get run. On why that's relevant, we'll get to later. But that brings us to our timetable. We are currently in the first part of our Mini-Symposium, where we start at 3 o'clock. That was 15 minutes ago. The first talk will be from Gustavo de Moraes about performance analysis. Second one will be from Anthony Leroc, queuing and scheduling. So last point here. And the after talk by Fabian Orland about debugging and correctness analysis of codes. Thereafter, we'll have a very, very, very short coffee break, 10 minutes, and then reconvene here, hopefully, for our second part, where Raphael will talk about software installation and why that is an issue. Sebastian Kreutzer will talk about performance analysis, number 2 thereof, and then William will talk about performance monitoring. Okay, so we chose a few talks here. The first one is from Gustavo about performance modeling for CFD applications using OpenFOAM as application and trying to get toward automated generation of runtime models for parts of the code. Code gets instrumented via SCORP, and thereafter extra P gets utilized for generation of performance models. Second one is our talk on the modeling and improvement of suboptimal submission patterns on HPC workloads by Anthony Leroc. Main gist here, we all need to specify runtime limits for our jobs. Please don't trust mine, they're off by a factor of 100, often. And so we somehow in some way need to get towards reliable runtime limits and thereafter queuing decisions. Then we've got our debugging talk, correctness and performance analysis of an open source CFD application by Fabian Orland, where thread traces are detected in the FEM code calculix, and subsequently we'll get a performance analysis and improvement of the code using SCORP. Then, of course, everyone's favorite, we'll have a coffee break together to thereafter reconvene for the talk accelerating the flow simulator towards a rapid or low effort deployment of HPC software by Raphael Haupt, who will show us how we handle 200 dependencies deep dependency stacks. Then go towards streamlining performance analysis workflows using compiler-assisted instrumentation selection by Sebastian Kreutzer. Goal here is not to write your SCORP instrumentation filters by hand. but get that automatically in the hopes of saving you as developer time. And last but not least, working towards fairness in performance data by William. That is about getting the performance data continuously for your specific program on a daily basis out of CI and production runs. And with that, I'm at an end here. And Ronnie, do you want to do the honors for IPDW?